Good morning. So today we're going to talk about the heat equation. And let's review some facts. Some of it I imagine you already know. So kappa is our diffusion coefficient. And let's start, and I should say kappa greater than 0. Remember that when we did the numerical case, I showed that depending on the discretization, it could make it negative, so that would be bad. Let's start with U and Rn. I mean, it's a scalar. But in Rn, so it could be, say, temperature or whatever. There's many diffusion problems. And let's take the normalized that is dimensionless. Without loss of generality, we could change variables. I'm not even going to worry about it and write it like this. Okay, so actually here I should have written already like this, sorry. Okay, so let's take the heat equation and we can do our Fourier analysis as before to see what, say, like the dispersion relation would be. I'm using the notation. I think now I'm following Fritz John, so for those who want a reference. But this is in many books, and Fritz John uses the wave number as xi. Okay, so I didn't change it. I usually use it, many people use it at xi, many people use it as k. I'm using it to keep the notation of Fritz John. I kept it at xi, where, xi, like this, is the wave number vector. Okay, so we already saw in that case when we're starting to understand the Eichner equation that the wave number can also be a wave number vector having the directions related to propagation. So therefore, we can write that I omega is equal to minus the absolute value squared of the wave vector. Okay? So what is this? We've seen this, right? What did I do? I'm not going too fast. I'm skipping something, but I'm not going too fast. The fact that I changed notation maybe might have confused you. That's okay. I mean, it's not okay that you get confused, right? I got to help you not to get confused, but it's okay that for a while. Look at this. If I had this, let me do a little, with our usual notation, this would say that I omega is equal to minus k squared. Okay, well, let me see here. No, yeah, but this is with a plus here. No wonder I was thinking I was something wrong, because in this case we put a plus. It doesn't matter if you put plus or minus. So look what happens. What do you see? You see that this is like the dispersion relation, right? Which is basically temporal frequency, how it relates to spatial frequency, where here is spatial frequencies in different directions, because just think of it in 2D, which is easier to visualize. C1, C2, which would be K1, K2. So there's a wave like this, as my arms are doing, varying in two directions. It might vary more slowly in this direction and more quickly in this direction, so it has two different Ks, right? Two different wavelengths. In this direction, it's purely periodic, but slowly it has a K1. In this direction, faster, K2, right? Because it's going faster like this. And we see that, therefore, that you've put here, you have an exponential decay from the dispersion relation. This is not a dispersive equation. It's not a hyperbolic equation. It's a parabolic equation. You have a decay of the wave modes in time. Okay? So we'll see this more clearly as we write things up. Anyway, so here, the next equation I have in the notes, I hadn't seen it, we can formally write this. So what does this say, right? If we read this with our applied math jargon, this says that I have a Fourier mode at time 0. The amplitude of the Fourier mode is 1. Right? If we were in one dimension, you can think of this as a sinusoidal type of variation of the temperature. If the problem is a temperature diffusion problem, but diffusion appears in many different ways. Right? As I mentioned to in one of the early classes of the course, you can have diffusion, apparent diffusion, for a wave over a randomly varying medium. Right? I'll try to wrap up the course going back to some of those figures. We're getting close to the end of the course. But let's read this. This says that a oscillating mode in space will decay in time. Okay? It's not propagating. Can you see this? This mode is not propagating. It's stationary, right? Because x, it's not a variable of x minus ct. So it's not a traveling Fourier mode. It's a standing Fourier mode that will decay in time. This is the amplitude of this exponential, right? Which might have different wavelengths in different directions, right? And look at this. The decay rate in time depends on the spatial frequency. Okay? So if I have a problem, if I have a wire, let's look at 1D. Okay, this is more complicated because here's in n dimension, but if we are in 1D and I have this and I have this is C1 equal to 1. This is Cn much greater than C1, right? Spatial variation, where C, just like K, is 2 pi over lambda. So if U is temperature, right? Note how things are sort of intuitive. If U is temperature, which one of these two rods, like piece of metal, will cool down faster? This one or this one? The dispersion relation tells us which one is going to cool down faster. Here it is. Come here or look at here. For the larger wave number means smaller wavelength will exponentially decay faster in time. Right? And it's kind of intuitive in this sense. At least my intuition is that, look, this is hot, this is cold. This is hot, this is cold. So the cooling down is much faster than this guy, the energy flowing from this whole part to that whole part, exchanging heat energy from that part to the whole part. That's at least my intuition why of this expression here. Okay? All right. So this is the decay rate for this Fourier mode. Okay? So the question I have here in the notes that I put here for myself first to remember is, what happens if I have the backward heat equation? Backward heat equation means for example, if I reverse time, that means backward heat equation. If I reverse time, So I can change variables here. T is equal to, substitute by to minus tau, right? A minus will pop up here. And that's the same as basically doing the backward heat equation is the same as doing negative heat diffusion coefficient. And I mentioned when we saw that numerical method sort of example that the diffusion coefficient depended on delta x and delta t plus some numbers, and it could be the sigma, the Courant number, could make the diffusion coefficient be greater or smaller than 0. For example, if the Courant number was bigger than 1, it would be then a negative diffusion coefficient. Look what happens. If I have a negative diffusion coefficient, or if I go backwards in time, so let me share my intuition with you. Look, if I go forward in time, things decay. So what do you expect? If I go backward in time, things grow. Exactly, you just did with your hands the correct thing. Things grow, right? Just change your time to minus time. Also, if I have a negative diffusion coefficient, right, this happens. So here, maybe let me help you. Here, if I did not dimensionalize, maybe that's a little bit bad of this exercise, if I had not dimensionalized the diffusion coefficient here, it would appear here. Okay, double check. That's an easy exercise. It would appear here. Okay? So negative diffusion coefficient or going to negative time makes the amplitudes of the modes grow exponentially. And they will grow exponentially in an unbounded fashion because c goes from 0 to infinity, right? So it's like when you do the Fourier transform, we're doing it in k. So if we're doing the Fourier transform, this guy goes to infinity. That means that the growth rate for negative time is unbounded. So it's a little bit like the problem of the interface problem. It's ill-posed because a very teeny-weeny perturbation like this, let me do a caricature, right? Something like this. Right, this is periodic, okay? Pretend this is periodic, okay, please. And in an amplitude, epsilon, super small, this guy, if I go backward in time, will go much faster than this guy, much faster than this guy in an unbounded way, right? So we get, the problem is ill-posed. So notice, problem is ill-posed for time negative and for kappa negative, which basically, it's the same thing to some extent, right? Because of rescaling and so on. Okay, so this is an important comment. And if you now go back to those classes I did for the numerical method with the numerical diffusion, numerical dispersion, blah, blah, this explains it, okay? All right. Let me maybe use this space here. So let's write like this, U, T, T greater than 0. Here's my initial distribution. Let me write this a little more properly like this. Right? T equal to 0. X in Rn. Let's consider F continuous. And let's do the Fourier representation of the solution. This is what we're about to do now. Okay? So since we are in Rn, usually, right, the coefficient of the Fourier transform, there's a bit of an ambiguity depending on how you put it, on which side. So, right, so formally, what we've been talking about, right, now I'm just summing up all, let me write it, I'm summing up all Fourier modes, okay, let me put it like this. And Fourier amplitudes, right? Because look, at time 0, I don't see this guy. This is just the Fourier transform of the initial, say, heat distribution. Let me call it heat just for the matter of communication, right? Because diffusion appears in many ways, even probability, right? There's diffusion processes and so on, so it doesn't matter. So these are the amplitudes, and as time goes on, as I turn on my clock, the amplitude of each mode starts decaying exponentially, and with the rate, the faster is the mode where this is the initial amplitude of the mode, right? Can you read it that way? Okay? This is the initial amplitude of the mode. Okay? So we're using, let me put, right, so that we have this correct. This is minus n over 2. This n here is not nicely written. Right, this is how we get the Fourier amplitude of these guys. So now we're going to play formally with these integrals, right? Admitting that we can do the manipulations, that, right, things converge properly and so on. So this is a Fourier representation of the solution of the heat equation, and this is the rule by which we do the Fourier transform, okay? All right, now, using these expressions, using the expressions above what we did, we have that u of xt let me write this like this. Okay, so it's manipulating the formulas. Put things together, but this is still a little bit ugly looking, but this is starting to look interesting if we can sort of clean up things, which is, I'm rewriting the solution. So you see, here the solution, let me put it this way. Here the solution is written in Fourier space. Okay? But not in closed form, right? As an integral in Fourier space, not closed. Then I go and write the solution in physical space, but not in closed form. This guy is ugly. This guy will end up being a kernel, will end up being a convolution. Right here it looks like a convolution, but we can't quite see it yet as a convolution. It looks like a convolution. So therefore, there's going to be some tricks to rewrite this. And do you remember what's going to appear here? I mean, have you seen this before? You know, it's going to be a convolution. And what is the kernel that will appear here for this capital K? It's a famous guy. Say it. No. Another famous guy. Not Poisson. It's okay. I mean, we're here to learn. The Gaussian is going to appear here. The Gaussian is the kernel of the heat kernel. Let's check this out. Okay? So I'm not going to do all the details. It's like tricks with integrals, blah, blah, blah. Some of it is already in the notes. I'll skip some of the details in the notes for the interest of us getting the interesting part communicating. So you agree, right? This is something, but this is a little bit ugly looking, right? It's not friendly looking. Not ugly. Not ugly. It's pretty. It's pretty. Math is always pretty, but it's not friendly in the sense I look at this and say, what is this, right? When you get the Gaussians, it's quite nice. Okay. So this integral can be evaluated by completing squares. Let me indicate where. Here. Okay? This looks a little bit like anyway, something that looks like a square, which is this. Let me write the result. I'll skip the intermediate part because you have it, right? So it's this. Can be written as this. Whoops, my handwriting today. Like this. This is T, where okay, so basically completely square, basically this guy, with that guy circled there, can be written, this is inner product, okay? So it looks like quadratic guys, okay? And that's going to be useful because then can be written, I'm also going to skip one step, okay? You can check this. I mean, it's in the notes, so it helps if one wants to do an exercise without seeing the result. Okay, so it's already starting to look good. So, in what sense? Using this change, the squares here, you can rewrite this not so friendly looking guy as this, which look, here's the Gaussian. Okay, this guy here, and this becomes also a well-known integral with tricks, blah, blah, blah. You break into products and you can compute it as this. Okay, it's not indicated here in the notes, but anyway, it's, I think in Fritz on the book, you have it. And this is, classic tricks with integrals. So therefore, putting all this together, we have this, which is really nice. And I'll say why it's really nice for many reasons. Let me highlight this with color. So this is, now it's so look, we see, I'm skipping some detail, but it's just like cranking the wheel, right? And some of the details are here. So we get that this now is basically, we see how this guy is. It is a kernel and it is a convolution. Excellent, right? So because then I can write that this, look, from here we can write that u of xt is equal to k convolved with f, right? Which in Fourier space also we have this, that multiplied by f, right? So let's see. These are the things which I think are very useful in many, many ways. So the kernel is now this Gaussian. Let me highlight another thing that we will double check. Let me drink some water. Let's see if you can, we're at the end of the course, you already know your teacher, your lecturer, inside out, you can guess what he's thinking. Why did I highlight this T in yellow? Right? Why did I care to highlight this in yellow? Look, this is a Gaussian. This guy here looks like something like this, right? It's a Gaussian. Say, I think you said it. Say it louder, Lucas. Yeah, as time goes on, this is where the place where standard deviation would be, right? So as time goes on, this guy becomes wider, the Gaussian kernel becomes wider and smaller, right? What is nice is that this guy here is scaled right so that it has total mass 1. And also, when time goes to 0 from above, you see what my hand is doing, right? It goes to a delta function. And basically, we're going to check this. And basically gives us back the initial condition as time goes to 0 from above, back to 0, right? Because this will become a delta function. It gives back the initial temperature profile. Okay? So this is correct. So you see the time here plays the role of sort of rescaling this Gaussian, okay? And as time goes on, this sort of it becomes broader, right? So it also feels better things on the neighborhood to some extent. We know that, and also, right, this is also showing that actually the parabolic equation, the heat equation, has a non-local aspect because this guy actually fuels everything, but in an exponentially small way as right to the border. If you're on the whole line, right, in an exponentially small fashion, right? But say, if I change the initial data far away, the kernel, quote unquote, knows that. Because this is the Gaussian does not have compact support, right? It effectively has, in the sense, effectively why? Because in the sense that it's exponentially small far away, but it's never 0, right? So the small, if I change the temperature 1,000,000 kilometers away, technically the formula knows it, but it doesn't affect anything, right? Because effectively it's small. Okay. Good. So let me mention one thing, because I certainly will not do this today, but leave this in your minds. When I did the problem of a wave over, say, this is a problem that came from acoustics, and then actually in my thesis I did this, and later on I did this for water waves. So if you have here a random bottom, so I mentioned this in that talk I gave through the presentation. Okay? So here the depth is varying randomly. Okay? The correlation length of the depth, say little l, is much smaller than lambda, the wavelength. There is a regime, right? There is a regime. Sometimes I give this as an exercise, a reading exercise in this course, or a seminar exercise in this course of papers, where there is a regime where this wave, after it has traveled for a very large time over this random bottom, this wave down here, it's a little bit like this, right? And to leading order, asymptotically, the front of this wave is given by, if this initial profile is F, is given by K convolved with F. But it's a wave equation. There's no diffusion. But because of the reflection transmission over all these very small walls, right? The wave goes back and forth, it generates a tail, a little bit due to dispersion also, but actually in the hyperbolic case, actually you can do this. For the hyperbolic case is which case? Is the acoustic wave. The acoustic wave is that hyperbolic system. You will see this tail, which let me put it in a better way as a schematic. It's not periodic, it's not like the airy function, it's a random tail because this bottom is random. So how you do this in the computer? You sample random heights using a random number generator. You generate this, you send away. And the cool thing, the nice thing, is that to leading order, asymptotically, I'm not giving you all the details, but some words you will understand, is using right and left going modes. You know what I'm talking about, right? There's things like that in the homework. Right and left going modes. In the Papa Nicolau, the Fouque, Garnier, Papa Nicolau, and Sona book, which is one of the reading exercises I gave you to, this is a problem treated there, and they show there, this is not an exercise for you, is that if the bottom is random, look how this is cool. If the bottom is random, to leading order, the transmitted wavefront is given by a Gaussian, more than this, I should say a Gaussian convolved with the initial wave. But there's no, in that equation, you're looking at this equation, right? That's the equation for the periodic case. There's no diffusion coefficient. So what the hell is going on? Well, what's going on is, it's very nice. So say it in your words. Say it, Louis, please. Yes, there's, very good. There's a wave going and coming back. So this wave that's moving this way forward is losing energy to the waves that are coming back. And if the scaling is right, this is not universal. It's for a certain scaling. For example, this is smaller than the wavelength. It cannot be also too small, but there's a certain regime where then the way this energy comes back and the way this front is shaping, how is it shaping? It's going down because it's losing energy, right? It's going down, widening, and it goes down and widening, governed by a Gaussian kernel. That's why it is called an apparent diffusion. Because there's no diffusion coefficient, there's no UXX, whatever, in the equation, in the PDE. There's no UXX. But it's basically this reflection mechanism that is mathematically very similar to a diffusion. And actually, in one of the papers that does not do a probabilistic modeling of this, a very nice paper by Berlian and Burge, sometimes I give it also as a reading material. This time I didn't give it, no, to vary, is that they call this a stratigraphic, I have to breathe and say it or else I cannot say this long word, stratigraphic filter. So what does stratigraphic means? Then in Portuguese it would be like estratigráfico, de stratus, of layers. It's a filter due to the layering. That's one of the titles of the book you're reading. The layering, right? Remember I mentioned here in the class, some classes ago, the reflection transmission by an interface and the reflection transmission that becomes very complicated by a layer. Here it's thousands of layers. And therefore, they call this a stratigraphic filter, or a filter due to many layers. That's the stratigraphic. And why is the filter due to many layers? Or let me ask you another question. What type of filter is acting here? Well, have you ever seen mathematically, it's very simple, but maybe you haven't seen it. I mean, a filter done in Fourier space. Yes or no? Maybe not. I don't know. I didn't see this for some time. So let me mention about this. Look, if I have a function f, this is x, and this is my function f. Okay? I do it a Fourier transform. No, this is k. Sorry. This is f hat. And let's pretend that the spectrum is something like this. Okay? So if I multiply in Fourier space this guy by this function here, or this is 1, I just multiply in Fourier space this by 1, what am I doing? I'm filtering out this guy. So this is called a low pass filter. Low pass, why? Because it allows the low frequencies to survive. So that's why low pass. Pass allows, quote unquote, low frequencies. So this is a low pass filter. So this is basically doing f times, let me put it like this, 1, the indicator function for this interval. If I come back in physical space, this is going to be a convolution, okay? And the Fourier transform of a square wave is a sinc function. So it depends on the way you go. So this is not so important, okay? So this is a low-pass filter. It's the simplest filter you can have because it's 1. It says, okay, everybody that's in this window, please continue. Everybody that's out of this window, bye-bye. You're out of the problem. Right? Isn't that what's doing? Now, what is this guy doing? What is the stratigraphic filter doing? The stratigraphic filter, instead of doing this, let me erase so I can stay here. And I'll write again. The stratigraphic filter, what it's doing is this. F hat. Okay, let me try to imitate the same function. Okay, this is the same function. But now, I erase this. This is, look, here it is. This is basically K convolved with F, right? But K is a Gaussian, so it's the same thing as K hat multiplied with F hat. So basically I have a Gaussian here. Okay, let's suppose the Gaussian, just for better communication, let's suppose the Gaussian here. No, let's leave it like that. So what does this say? And let's suppose the Gaussian here is so small that it's almost not important. This is also a low-pass filter, right? This is also a low-pass filter, but that does not really cut anybody. But it says that, hey, if you're outside this wave band, you're exponentially non-important. And the most relevant modes for the dynamics are the ones more in this region, right? So that's why this problem of the wave that I just erased like this over the layers, the random layers, right, was called a stratigraphic filter with a Gaussian profile. So this apparent diffusion, if you don't like, André, I don't like calling it apparent diffusion because there's no diffusion coefficient in my equation. Okay, then you can call it a stratigraphic filter because mathematically it's the same thing. It's basically a Gaussian convolved with the function. Okay? So those are things, see, at this point, without doing much, right? I didn't do much of heat equation, but without just being here right now, I can already tell you a little bit the story of things I told you before, showing pretty pictures, but you had no reason to understand what's going on. You still are not seeing the details, right? You still do not have to understand how does a Gaussian appear for the wave problem similar to one you're doing for the homework, right? Which is the reading homework, but you already have a little more, right, information of what's going on. Okay, let's keep on going now. Back to standard heat equation. So, okay, so here's what we want to do. Let me double check if that's what I have in mind. Yes. Something similar we did for the elliptic problem. So let f be continuous and bounded in Rn, then okay, so now I'm going to sketch the proof, right? Some parts are simple, some parts are just slightly tricky, but it reminds us very much of what we saw for the elliptic problem, where there we had the Poisson kernel, right? In the elliptic problem, we had the Poisson kernel. Here we have the Gaussian kernel. So we constructed this with Fourier manipulation, so we want to check now, is this guy indeed satisfy the heat equation and satisfy the initial condition for continuous F, okay? So procedure to prove this uses certain properties as follows. So similar to dividing it into steps, some steps very simple, some other not so difficult, but anyway. First one, the kernel is smooth. For positive time. So this is something already that's very nice. For example, if you start with a heat temperature, heat problem in temperature distribution like this. Right? What does this mean? I start with a bar, say a rod, I heat it up on some part, in another one, in such a way that times 0, it has a discontinuity. Here's at a temperature, here's at another one. Okay? So say here is U1, here is U2. Right? But as soon as I switch the clock on, this is smoothed out instantaneously because, you see, as soon as I switch the clock on, this guy that at time 0 was a delta function, as soon as it is on time 0 plus, as we write, right? As we usually use this notation, right? 0 plus, that means we just let go the stopwatch. This is a very skinny, tall Gaussian, but it's infinity, smooth, right? So of course there's going to be a very sharp transition, but smooth transition for the temperature. And this guy here, for time positive, is smooth, right? So that's not difficult. So this is a smooth heat kernel. And then B. So for time 0 plus, the kernel satisfies the heat operator, which is basically if things are okay, the function's okay, this guy decays exponential, whatever, we can throw in exchange because this is an improper integral, we can throw things inside. So if we can do all that, right, it's easy to check. Another thing that's obvious, that's super easy, it's a Gaussian, it's positive, right? In particular, for time greater, D. So for any time positive, it has total mass 1. So that's why also you see sometimes these guys appears, right? It has to do also like a normal distribution, a measure in probability, right? The Gaussian has total mass 1, no surprise. Okay, and then E, something a little more technical, but it reminds us what we did for the elliptic problem with the Poisson kernel. So when these guys are separated by a delta, this goes to 0 uniformly. In X, so D plus E combined will imply a delta Dirac function as time goes to 0, right? And in the notes there, it is done, I'm going to check it here, checking property E. And therefore, we get also, right, with this, the initial condition. So I'm not giving all the details, but I'm giving the steps, the relevant steps for the proof, and it's very similar to the thing. So so it's also in the notes. So check if you want, as a good exercise. Don't look at the notes, do it as an exercise. Whoever's watching, check that initial condition is satisfied. Okay, with all these facts. Delta function, this uniformly coming down, and you will see that then this gives us back F, right? Okay, good. So I have my last half an hour to speak something I planned today, which is starting mention. I probably won't be able to finish. I don't know. We'll see how far I go. I don't want to rush, but not finish. Now, how do we use many of these things? So this is a little bit our review. It's kind of a review. Maybe not. I mean, it's good to get feedback from you, right, my audience here, that because we see, at least I saw, heat equation for the first time as an undergraduate as how? Separation of variables, right? You put something in space, something in time, but that's a little bit how you get things with eigenvalues that kind of relates, as we showed already, that eigenvalues kind of relate to dispersion relation, right? We saw this. Okay. Then this is a nice way to see the heat equation, particularly because we get to this Gaussian, the fundamental solution, right? The Gaussian kernel that also can be interpreted in many ways, including as a filter and this and that. I mean, I don't know if this is new for you, seeing the heat equation done like this. No, right? So this is pretty much standard defined in many books. And I won't get much more into the heat equation itself. Now I'm going to go to viscous burgers in one dimension. Okay? Because then I think maybe something you haven't seen. So now what we're going to see okay, so here in heat equation, the novelty is also this thing about waves in random medium, whatever. And in this course, at the end of the course, is basically a little bit of information, cultural information, because we're not doing all the details. But it's good for you to know that such a thing exists, and that actually the result of the Gaussian kernel can be read, interpreted in many different ways. Now let's look then at Burger's equation, which is an advection diffusion equation. Okay, here it is. I'm going to write it like this. So here's the advection term. Here's the diffusion term. I also call it sometimes the viscous Burger's equation, or this was actually the original Burger's equation. Now you know about it. And what we're about to do is we want to see the Kohl-Hopf transformation. Okay, so this has in Witham's, other books I mentioned here, Kevorkian. So this is something from the 50s. That these two applied mathematicians, I think, kind of independently, I think up to where I know, right? Two well-known, I mean, Hopf and Julian Kohl, they did this, which is, look, I think this is how they probably thought, right? This looks like a heat equation, but it has this nonlinear transport term. And there are equations, so two things. I always like to ask if you know or don't know as curiosity. Who has seen here knows what the Kohl-Hopf transformation is? No. Okay, good. So we have something to learn. Now, here it has a flavor. It has a flavor that, at least to me, reminds me a little bit when one learns how to solve an ODE called the Riccati equation. Who has heard here about the Riccati equation? Also no. Okay, so the Riccati equation, where it checks, sometimes appears in waves in reflection transmission problems, but in a more complicated way with variable coefficients. But the original Riccati equation is a nonlinear ODE. Just so you've heard this before. It's a nonlinear ODE that actually you can do this change of variables, similar to this one. That's why it reminds me. A change of variables that the nonlinear problem becomes a solvable linear problem. Cool, right? So you do a change of variables that the complicated nonlinear problem. So look what we're going to do here. The idea is the same. I would suspect this inspired these gentlemen. So look at this. Transformation uses the following change of variables. U now is going to be, minus 2 epsilon Vx over V. Okay? So it reminds me a little bit the Riccati change of variables that I don't remember off the top of my head, but something a little bit like this. You create a new variable and you divide it by its derivative in some way, whatever. A little bit looks like a logarithmic derivative, right? So you do this, okay? You do the change of variables. It's here in the notes. I'm not going to do it, right? So you check. So find what ut is equal to. ux is equal to blah, blah, blah. And then you substitute. In substituting, burgers becomes this. Okay, so you have to just chain rule here, okay, and substitute. It's easy. I'm not going to do it, waste our time here. So what is cool about this change of variables? What do you like what do you like about this change of variables? We have this nonlinear problem, and what we get out of it. No? You're not happy with it? You don't seem happy with it? Well, now, if V, our new variable, satisfies the heat equation, I'm done. Do you agree? Look in parentheses. Oops. No, sorry, I wrote it, my mistake. Sorry, I'm not fair. I went too fast. Okay? But anyway, if V satisfies the equation inside the parentheses, we're done. In this case, it's the heat equation. I had written before it would look like a Helmholtz equation. Sorry, but it really doesn't matter so much for the question. So you see, if this is 0, this will also be 0, and boom. If V, so then what I have to do now is make V, find how to make the proper problem for V, solve the heat equation. We know how to do it. And then use this, and I've solved the Burger's equation. You see, if I solve the heat equation, I get the solution. I differentiate it by x. Divide it by itself, I have the solution of the original problem. Cool, right? Very nice. Okay, so if Burger's equation, I have to put this here. So if this is my problem for Burger's equation, right, then for Koh-Hopf, I have So, of course, nothing in life comes for free, right? We know, right, the expression we use in Portuguese, also the short blanket scenario, right? You want to cover your feet, you want to cover your head, the short blanket, cobertor curto. So, but you got to take the benefits of your short blanket. What is your priority? So, for this problem could be very difficult, so you're gonna break it into two simpler problems. So instead of one problem, you have two simpler problems. So the first one is to get the new initial data for V, you need to solve this ODE, right? You have the initial data VF. So F is equal to this by the change of variables. But now, what is the initial condition for V? You have to solve this ODE. Okay, not so bad. If you solve this ODE, then the answer for V is done by the Gaussian kernel, blah, blah, blah. We're done. Okay? So, well, this ODE, you can use an integrating factor. So you can write this. So it's not so bad. It's actually the short blanket is not that short. which for short, I'm going to call this like this. Right, the constant C, the same. Oh, no, they're different because there's the other one coming from 0. Okay. Okay, so let's call this, right, you can do this, let's call G this whole junk that appears from here. So that, right, we don't have to carry this guy along with us. Okay, let me erase this so I can use this space here before I go way to the other side. And look what we have. We have then that Vt is equal to epsilon Vxx, where Vx0 is equal to C G of x. We already solved this problem. Piece of cake, right? So V of x, t, sorry, is equal to C 4 pi epsilon t, integral from minus infinity to infinity, g of y, e of minus x minus y squared over 4 epsilon t, dy, right? We already know how to solve this. V of x, if you can formally differentiate this guy, okay, we have this. Very simple. But now, I mean, we're solving the problem, but then, now we have that here's the solution to the Burger's equation. Right? This is correct. I already see that some of you maybe don't like it because it does not look, it's correct, but it does not look pretty, right? So see is it clear what we did, right? You start with this equation, it's nonlinear, has the diffusion term. Can I get a free ride on something we already did? Yes, we can get a free ride with this tricky, smart change of variables. You get that then V only has to satisfy the heat equation. And actually, the only new part of work, I said two, but the only new part of work is solving this OD, which is also not that difficult. You get an integration factor, blah, blah, blah. Call this guy G. So you see, this G in here is already this junk here. But fine. Leave it like that. It's fine. And solving this problem, doing back the change of variables, here's the solution. So everything is correct. Everything is good. Right? So there are many questions that comes to our mind. Okay? So one question is, say, when epsilon goes to 0, what happens? Okay? Which is basically a question of interest in mathematical analysis sometimes, which is if this regularization term goes to 0. Remember I mentioned to you that the diffusive regularization of Burger's, because Burger's has a shock, the diffusive regularization of Burger's is usually a classical regularization in the sense it converges in the strong form. Epsilon goes to 0, and you see the solution over it. And there's that case which I showed of the hyperbolic tangent, which is a special case. This is a more generic case, right? And through what we will see, I don't know if I'll do it today. I don't have to rush. I can always end a little bit early and we continue this next week, is this, what we need to do now, and I'll give you also a very quick short course, not even a short course, just a very quick like sort of brush of paint, so you see it, is what comes in now is another asymptotic ingredient that in this course I mentioned a few of them. In this course, I mentioned this last time. I started with asymptotics of differential operator, how we do reduced modeling, right? Then I mentioned a little bit asymptotics of solutions, how we do averaging, right? Now there's another flavor of asymptotics of solutions that goes to something classical, old, that goes back to Laplace and many other guys, which is asymptotics of integrals. When the integral has a small parameter or a big parameter, right? Sometimes here it's 1 over epsilon that's important, or it's epsilon. We'll see, right? We'll see this. I think I'm going to leave this for next class. So what I need to do, and this is very common in these problems of solving PDEs, is that sometimes we can write formally the solution. But what I told you from the beginning of the course is that the goal of this course is actually to have an idea how the solution looks like. Right? Sometimes in functional analysis, which is important, you say, oh, it has 1 or 2.5 derivatives because those are the estimates in Fourier space. But that's important, and it's a theorem, prove things, right? But you don't see exactly how the solution looks like. It has 2 derivatives. You have regularity. It's well posed. But how does it look like? Here, you get this. You can do the limits as epsilon goes to 0, right, in the asymptotics. But we want to see also a little bit how the solution looks like and so and so. So this is the goal, which I'm going to leave for next class, is to do now to show to you at least 2 typical asymptotics of integrals. Have you ever seen, again, this is for my own pleasure to know what you've seen before. If I talk about asymptotics of integrals, what are names? Have you seen this before? And what are names that comes to your head, to your mind, right? That is keywords, right? Keywords could be a name of a person, or it could be a keywords. I mean, to me, 2 things come to my mind, which I'll give you a brief introduction to you and a reference, a very good reference. Then if you need it, you work it out, you study on your own time. As I see here, nobody doesn't call for anything, or does it? So here are 2 names that maybe you have heard, but it doesn't connect. So one is called Laplace's method, right? So you see this. And the other one is called stationary phase. So you see, stationary phase already has 2 ingredients that that's why the whole course starts getting together. Looking at waves, you have learned what a phase is, right? And a stationary phase is when a phase has a stationary point, meaning derivative 0. And you're going to see that when we have an oscillatory term, here it's more like Laplace's method because the exponential is decaying. But there's another case where it's a Fourier transform where the exponential has a I, so it's oscillatory, and then stationary phase is the method instead of Laplace's method. Don't miss next class because I'm going to just give you the highlights, very brief highlights of that, because then, if you need it, you will learn. And these are classical methods. I mean, they exist, right, some of them for more than a century, like Laplace's method or whatever. Okay? So let's see what else I want to say. Yeah, I mentioned here exactly. So next class, I'll show to you how do we make this guy here that looks unfriendly from my goals in applied math, that is to see a little bit how this solution looks like. This guy is a very good step. This trick is super nice, but I'm not super happy yet because I want to see a little more how this guy looks like. And that's the asymptotics of integrals, which we'll see next class, which is exactly the next sheet I have in my notes. We have like 15 minutes. We're getting close to the end of the course. There's no reason for me to start today a little bit of integrals, and I'm going to do this next time. But let me just then write you one thing. Here's what Laplace's method is. I'm going to just write this. Okay? And, for example, one regime of interest is for large M, for this problem. This is the notation of a complex variables book, which I like a lot. I mentioned to you, but it has this because many of these use, which is the book of complex variables by Ablovitz and Focus. Even though if you look for in the library of your university or here at IMPA for books on asymptotics of integrals, it's a classical topic. There's books just on that, or there's other books that has chapters on that. And this is a complex variables book, which I like a lot, that has a chapter on asymptotics of integrals. So you see this integral as m goes to 0, sorry, as m goes to infinity, becomes big, this guy looks like it's 0, like it's not interesting. But depending also on the behavior of this function and so on, you can get some interesting approximation. But we're going to talk about this, a little bit about this, next class. Okay? So I think I'll stop here, right? We're getting close to the end of the course, 15 minutes, a little bit ahead of time. And then we start from a good point next Monday. So, and we'll see. I'll see how much in these. I have 2 more weeks, but maybe I don't know. Because starting something or rushing something might not make sense. So we'll see. I'll let you know next week if we finish next week or whatever. Okay? But we're getting close to the end. Okay.